So just to recap, what we've been talking about were ways to describe a function. So we've talked about domain and range. We talked about positive, negative, 0. We talked about increasing, decreasing, and constant. We talked about extrema. We've talked about end behavior. And our last one, Clayton? Sure. This is all previously. We've talked about these topics. Our last description is going to be a lengthy one. We won't finish talking about this today. It'll wrap into next class. So the last way we might describe our function is as a transformation of a parent function. Now there's a lot of vocabulary in that that is probably unfamiliar, and that's okay. We'll unpack this statement like one piece at a time to kind of give us an idea of what's going on here. And I'll kind of explain conceptually what it is that we're doing. But then at the end, we'll kind of wrap it up and be like, okay, this is what I actually need you to be able to do, and how we use what I'm about to explain to do these kinds of things. So some of what I'll do here in explaining what this is isn't things that I would expect you to be able to repeat. And I'll try to be very clear at the end with like, okay, this is what I actually need you to be able to do. But I think it helps to kind of see where things come from, rather than like, here's a bunch of rules, and this is what I want you to be able to do with them. But rather kind of see where these things come from a little bit. And I'm going to do that here today. Well, start that today. So the first thing I want to talk about is this word transformation. So in your geometry class last year, you talked about different types of transformations. So you talked about 4 main types of transformations. Only 3 are going to be relevant for this class. The first is called a translation. And what happened in a translation is you took like a shape and you basically like moved it to a new location. So notice the size of the shape remains the same. The shape itself remains the same. The orientation, the direction the shape is pointing, stays the same. The only thing that changes is its location. So it's basically you picked it up and moved it somewhere else. You can move left and right, you can move up and down, or you can move a combination of like right 4 and up 6 or something. You can do both. Everybody okay with that idea? So if I have a generic point here, let's say that it's xy, and let's say we moved 5 units here to the right, what coordinate changes when I do that? The x coordinate. And what does it change by? 5. So the new coordinate would be the old coordinate plus 5. Right? Would the similar thing happen if we also moved up and down? But it would be the y, exactly, that we'd be changing. Do we have to change the same for the x and the y? Could I go 3 over and 5 up? Yeah, definitely could, right? So for a translation, we are adding or subtracting to the x or y coordinate. Everybody okay with that? Remember that from geometry last year? This was an easy to remember topic because it's usually very visual. There's not a lot of theorem built around this. The second type of transformation you would have talked about is a reflection. So imagine you had this triangle and you reflected it across, say, the x-axis. So notice here that the shape itself stays the same. The size of the shape stays the same. The location is now different. And potentially the orientation is still different, or is now different. The orientation, depending on the shape itself, may or may not change. Right? If this was a square, it's still it's oriented kind of the same way still. Unless you name the points, like A, B, C, D, and then you'd see some orientation change. So in this case, if this is a generic point x, y, how do the points change into when we have the blue triangle? So which coordinate changed, x or y? The y, and how did it change? Became negative, right? And if I reflected across the y-axis instead, what would change? The x-coordinate would become negative. And can I reflect across both? Yes, right? It would just end up like over in here, right? If I did one and then the other. Okay? When we say negate like that, what is that equivalent to? Like what operation? When I say operation, I mean like your 4 basic operations like add, subtract, multiply, divide. It's not subtract.
Not subtract. Nice try.
So it is the same thing as multiplying or dividing by what number? Negative 1, right? So you could say divide. Usually we write it as a multiply. Everybody's okay with that idea? God bless you. Okay. The next type of transformation is called a dilation. So when you dilated something, or bigger, the size changes, the shape remains the same, the orientation should remain the same, the location could change, at least for some of the points. So again, if this is a generic xy here, What did we do to the x and y to change or to do this dilation? What operation? Add, subtract, multiply, or divide. Multiply or divide, yep, by some factor. I'm going to call that factor k in this case. So in your geometry class, you saw that that factor was always applied equally to the x's and y's. I don't think you looked at a situation where you did a different value for x and a different value for y. Is there any reason that you couldn't do that, mathematically anyways? No. The reason you didn't do that in geometry is because the resulting figure is no longer similar, which is, I think, what you're using dilations to kind of talk about or get around to with similar figures. So if you do that, you lose the similarity, but that's not important to us in an algebra class, so we're not so concerned about that. So you could multiply the x or the y by the same or different quantity. So you could multiply the x by 3 and the y by a half, and you could do that. So here we're going to be multiplying the x or y coordinate. Is everybody okay with that idea? Now, in your geometry class, we looked at these transformations in regard to a shape, right? Like a triangle or a square or a circle or something. But remember, these line segments contain infinitely many points, right? So a triangle is really a set of ordered pairs, it's just a bunch of points, which is kind of like our description for a function, right? So there's really no reason that we can't apply the same ideas that we've talked about here in geometry of translation, reflection, and dilation to a function. Because a function is just a set of ordered pairs. We don't usually think about it in that way, but that is the way, or part of the definition we gave for a function way at the very beginning of the semester. So that's where we're going to start tomorrow. We see you again tomorrow, right? So we're going to start tomorrow off is picking up